on stochastic integral for SPD, A compared.
Thank you. Let me begin by thanking the organizers for giving me the opportunity to present this lecture, and also for inviting me to stay at the Newton Institute, where I've really enjoyed my time, and it's been rather productive and interesting. So I'm speaking on stochastic integrals for SPDEs, a comparison. This is based on a joint paper with Lluis Quer-Sardanyons from the Universitat Autònoma de Barcelona. What will I be talking about? So the objective of this lecture is to compare stochastic integrals that are commonly used to study stochastic PDEs. So in principle, almost everyone in this room will have used one of these integrals. Most common two, I would say, are the ones that come out of Walsh's theory of martingale measures with various extensions that were developed over the years. Or people have studied the sort of Krylov-Rozovsky to Prato Zabczyk theory of Hilbert-space-valued stochastic integrals. And typically when a student enters into the subject, they learn one or other of these approaches, and both are difficult enough for most students that then they never learn the other one. And that was the case for me, essentially. So this is not a historical comparison. I realize, I put some names here that correspond to important books that were published, but I'm not trying to say that these people, certainly were involved with the theory, but others were too, such as certainly Pardu and Gionji and others, many others. And I'm not trying to say that one integral does better than the other or whatever. I'm just trying to say, what can you integrate with one theory, what can you integrate with the other? How are the results related? If you use them to solve SPDEs, do you get the same solutions or different solutions? I'm not going to teach you either theory. I'm assuming you know at least one of them. Why am I doing this? I'm not really an expert on stochastic integrals. I just use them to study SPDEs. The motivation came from a comment of Michael Ruckner, who at a meeting in Stockholm a couple of years ago, after a lecture by one of my former graduate students, said, well, it would be really nice if somebody compared these two approaches so that everybody would understand what everybody else is talking about somehow. And so we took that comment to heart, and that's what made us write this paper and is leading me to give this lecture. And I'm only discussing the most basic integrals that essentially everybody uses, at least from time to time. I'm not discussing the many more sophisticated types of integrals that are out there. And here I've just listed a few of the names: Mikulicz, Rozovsky, Brezhniak, Van Erven, Weiss, and probably many others that develop more sophisticated integrals that are needed in various specific situations. The types of SPDEs I have in mind, so the integrals I'm thinking of them as being useful for certain SPDEs. The type of SPDE I want to consider is essentially the heat and wave equation, which you can combine here into a damped wave equation. With a second derivative in time, a first derivative in time, a Laplacian, and then here on the right-hand side, a noise and various nonlinear functions, sigma and b. T is time, x is in Rk. You need certain initial conditions. If c equals 0 and nu equals 1, so if I specify the two parameters here, 0 and 1, I get the heat equation, or I can specify 1 and 0, get the wave equation. Those are the two cases I'm most interested in. But you can combine them, put them together. And then, SPDEs, stochastic PDEs, comes typically when you have here a random forcing. And so the types of random forcing that are most commonly used are space-time white noise. And so this is a Gaussian process where the covariance is written here, where delta 0 is the Dirac delta function. So that's the most commonly used noise, but it has certain limitations that you can't then study SPDEs in higher spatial dimensions. And so people use other noises, and another noise that I want to consider and essentially focus on is spatially homogeneous noise. So this is an extension of space-time white noise, and the covariance is given here. It's still white in time, but then there's a correlation in space given by a function f of x minus y, or it could be slightly more general than a function. Okay, so I essentially want to think of integrals that are useful for the stochastic heat and wave equation driven by spatially homogeneous noise. And let me say be a little bit more precise about this spatially homogeneous noise. So I'm going to think of this as being a generalized Gaussian random field. So a family of Gaussian random variables, W of phi. Phi runs over a set of test functions. Here, C infinity functions with compact support. And so you have to specify this Gaussian family by giving its covariance functional. And so the covariance functional can more generally be written in this form. So lambda is typically a measure and even a non-negative measure. Here I have the convolution in the spatial variables of a function, the function phi that appears here and the function psi here. The tilde is just to say psi tilde of t is psi of minus t. And this function here, this functional of phi and psi, has to be a covariance functional. So that imposes certain conditions on lambda. And typically lambda has to be the Fourier transform of a non-negative measure. And that measure I'll call mu is the spectral measure, a non-negative measure. And lambda is the covariance measure. So these are two equivalent ways of writing the covariance functional for spatially homogeneous noise. The typical choices of lambda are, for example, f of x dx, so a measure that's absolutely continuous with respect to the Lebesgue measure. And then this expression here just can be written as I had on the previous slide with this function f of x minus y. Or this measure lambda could be the Dirac delta measure at 0, and then I would get back the space-time white noise with this formula here. Okay, I guess we all know that you need to have stochastic integrals to study SPDEs. Let me just briefly remind you why. So here I have a partial differential operator, and I consider the SPDE, the partial differential operator is L. Lu equals some function times noise. There could be other terms. Let's just think of this term. And so I'm going to multiply left and right by a test function phi, and integrate. Okay, this is the natural thing to do. Of course, already here you have to ask yourself, what is this integral on the right-hand side, this w dot of tx dt dx? Already here you need a stochastic integral of some sort. If you do a few formal manipulations without worrying too much about what the integrals mean, you very quickly end up with this so-called mild formulation, that is u of tx will be a term that is only related to the initial condition, so the solution of the homogeneous partial differential equation with the same initial conditions that I had for the stochastic partial differential equation. That's this term I0 of tx. And here I have this function g, which is the fundamental solution associated with this partial differential operator. Okay, and here I'd have the sigma times the noise. I still have here a stochastic integral that needs to be defined. Okay, but this is sort of the generic setup that you end up with when you study a stochastic PDE, is you fairly quickly get to this mild formulation. You have something that depends only on the initial conditions and the solution to the homogeneous PDE with those initial conditions, and an integral of this form where you essentially have a convolution of the fundamental solution, the nonlinear function here that multiplies the noise, and the noise itself. And you need to define this stochastic integral. What are these fundamental solutions? So if for the heat equation in all dimensions, we simply have the Gaussian kernel. So I'm on the space Rk. So this is a nice smooth function, except possibly when t is 0. In the wave equation, the situation is a little bit different. The nature of the fundamental solution changes according to the dimension. So in dimension 1, you have a bounded function, though not a continuous function. In dimension 2, you have an unbounded function. And in dimension 3, the fundamental solution is actually no longer a function, but a measure. So here there's this 1 over 4 pi t times the uniform surface measure on the boundary of the ball with radius t. Total mass of sigma is 4 pi t squared. So the total mass of the measure G3 is t. Okay, and in higher dimensions you also have explicit formulas, but the fundamental solution gets less and less regular. And so what we need to define, thinking back to the mild solution, are stochastic integrals of this form. So we have the fundamental solution G, which could be for the heat equation or one of these for the wave equation. Z is some process which plays the role of sigma of u, so u being the solution we're looking for. But initially you just want to define a stochastic integral of this kind. And then here you have the noise. Okay, so we want to define integrals of this kind, which I'll generically write v of g and z, g the fundamental solution, z some sort of process or random field that appears here. And so, as I was saying, the most common stochastic integrals I'll call the integrals from school A or school B. And school A, starting with the Saint-Flour notes of John Walsh, which were published in '86. The school was 2 years before that. Or this other Hilbert-space-valued Brownian motion developed over a period of years. So these are the dates where two important books were published. People nowadays often refer to the book of Prato and Zabczyk, but obviously that book came after many years of research by many people, and this book obviously came after many years of research also. And so what I'm telling you should remind the senior people of the good old days when they were in school in some sense, and the junior people should be more recent memories. A related approach, which is also well known, but maybe less cited in some sense, is a book of Métivier and Pelomai, where they discuss the integral with respect to cylindrical Brownian motion. And I mean, certainly these other groups were aware of this and used it. But I want to start with that because I think in the end this is a really basic and fundamental type of stochastic integral. So let me start with cylindrical Brownian motion. So we start with a separable Hilbert space V and a symmetric self-adjoint non-negative definite bounded linear operator Q on this Hilbert space. And the cylindrical Brownian motion will simply be a family of random variables, bt of h. So t is time, h is in this Hilbert space. And it'll be called a cylindrical Brownian motion on V with covariance Q if there's these two properties. So for any fixed h in the Hilbert space, as time varies, we have a Brownian motion with variance given by t times inner product of qh with h. And then these Brownian motions are related to each other by their covariance. The covariance of bsh and bt of g is minimum of s and t times inner product of qh and g. And in the special case where q is the identity operator, this will be called a standard cylindrical Brownian motion. Okay, so this is a very natural object since it's just a family of Brownian motions that are related to each other. And now we want to define a stochastic integral with respect to a cylindrical Brownian motion. So we introduce this other Hilbert space V sub q, which essentially you start, or for elements of V, you just take the inner product of QH with G when H and G are in V. This gives you a pre-inner product, and in certain cases you'll have to take the completion to actually make it a Hilbert space. Take the filtration generated by the cylindrical Brownian motion, and now we want to define a stochastic integral, so we start with a complete orthonormal basis of this Hilbert space VQ. And what we'll be able to integrate are square integrable functions with values in this Hilbert space. Okay, so G is a random square integrable function with values in VQ. And the integral is defined in the following way. So G takes values in VQ. We take the inner product with a basis element, so just the coordinate of G in the basis, in the complete orthonormal basis. As S varies, this is now a real valued process, which we integrate using an ordinary Ito integral with respect to the Brownian motion Vs of Vj. And then we add all this up, and because we've chosen G in this space, the series converges, and we have defined a random variable. Okay, and it has this nice isometry property. The expected square of the stochastic integral is the integral of the norm of g squared. This is the sort of property that you like to have for a stochastic integral. And let me just emphasize that this integral produces a real valued random variable. So the result of this operation here, g dot b, g integrated with respect to b, is a real valued random variable, even though g took values in this Hilbert space. Now, I want to use this for spatially homogeneous noise. Spatially homogeneous noise is not a priori given as a cylindrical Brownian motion. It was given as a generalized Gaussian random field, whose covariance I've written here again, using the spectral measure. So if I want to apply this theory of integrals with respect to cylindrical Brownian motion to spatially homogeneous noise, I first have to build a cylindrical Brownian motion from my spatially homogeneous noise. So I have to do a little first step. And you can do that in the following way. So let me take the completion of the short space of C infinity functions with rapid decrease under this inner product, okay, where I'm using the spectral measure to create the inner product. Here I'm taking the Fourier transform of phi and the Fourier transform of psi complex conjugate. And so this becomes a Hilbert space that may contain Schwarz distributions. It depends on the spectral measure. So in certain cases, it will only contain functions. In other cases, it will contain objects that are not functions, but that you can interpret as Schwarz distributions. And now I need to define a W sub t of phi to have a cylindrical Brownian motion. And so what I want to do is just take my spatially homogeneous noise and plug in this function indicator of a time interval times the function phi of the space variable. But that was not initially part of the definition of the spatially homogeneous noise, so I have to approximate this function by C infinity functions with compact support. Okay, so there's a step to do to approximate this function indicator times phi, which is not C infinity with compact support, by such functions. Okay, so you do that step, and then you have built a standard cylindrical Brownian motion on the Hilbert space U here, with this inner product here, and the covariance operator is the identity, so it's a standard cylindrical Brownian motion. Okay, so once I've done this, I can use the integral with respect to cylindrical Brownian motion to integrate with respect to spatially homogeneous noise. Okay, so now let me come to school A, and then I'll come to school B. So school A being the Walsh integral from his lectures in Saint-Flour in 1984. So Walsh's integral is based on the notion of martingale measure and even something called worthy martingale measure. So this is an object, mt of A. T is time, and A is bounded Borel sets. And if you fix the Borel set A and you let time vary, you have a martingale. And that's a nice thing to have. I mean, remember that Walsh with K. Rowley wrote papers about stochastic integrals in the plane and so on. So you like to integrate with respect to martingale. But you also have the spatial variable, so A is there to deal with that. And if you fix T and let A vary, you have a measure, so an L2 valued measure. And now you have to say, if I take different sets, how do these martingales relate to each other? So there's the covariance measure, which is a signed measure Q such that the covariance of mt of A and mt of B is given by Q of 0t times A times B. Okay, so a measure that tells how these martingale relates to each other. And what gives the martingale measure the qualification worthy is when there is a dominating measure. So sometimes a martingale measure will have a dominating measure and sometimes it won't. When it does, it's called a worthy martingale measure. The dominating measure has to be a non-negative measure, and it has to, bound from above absolute values of the covariance measure. Okay, so that's the basic setup. And then what can you integrate? So you write integrals of this form, f of tx integrated with respect to the martingale measure over time times space.
Can you take k equal to q on the previous slide?
You can't, if q is non-negative, then you take k equals q. But if q is a signed measure that is not non-negative, then you can't take k equals q. Thank you. So you can integrate random fields that are predictable with respect to the natural filtration of the martingale measure. And the condition that has to be satisfied is this condition here. So you have to integrate the function f with respect to the dominating measure. And as you see here, it's f of tx, and here it's again t, but no longer x, but y. And you're integrating over 0t times rk times rk. Okay, so you have this condition, which is a bit restrictive, but which means that you can develop the integrals sort of like you develop Lebesgue integrals and so on. Sort of a nice condition, or simple condition. The result of the integral is a real valued random variable, so just as for the cylindrical Brownian motion. Again, spatially homogeneous noise is not immediately given as a martingale measure. So if you want to use this integral for spatially homogeneous noise, you have to first build the martingale measure associated to your noise. So again, this will be done by a limiting process. The spatially homogeneous noise was defined for C infinity functions with compact support. You sort of approximate indicator of 0t times the set A in space by such functions, at least when A is simple, like a rectangle, and then you extend to bounded Borel sets by sigma additivity. Okay, so you have, again, this first step to go from the spatially homogeneous noise to a martingale measure. And then what can you integrate? So in the case where lambda is non-negative, as I've been considering, then the covariance measure is the same as the dominating measure, and you can integrate functions, I'll call them elements of P+, simply functions that satisfy this sort of condition. Okay? And this, if you're thinking now back to our stochastic partial differential equations, this will be sufficient to handle the heat equation in all dimensions, because remember the fundamental solution in those cases was a function. And it will be also sufficient for the wave equation, but only in spatial dimensions 1 and 2, where the fundamental solution was a function, but in dimensions 3 or more it was not a function. So if you're interested in the wave equation and going higher than spatial dimension 2, this integral by itself will not be sufficient. And so that was a motivation for developing an extension of this integral. And so I worked on that, and Nuellart and Quer-Sardanyons worked on that. So this is an extension that still produces real valued random variables, but you can integrate slightly more than functions. So this is the type of integral that we were interested in, convolution of the fundamental solution of random field Z and a noise or a martingale measure. And so here we're able to integrate elements that are subsets of the Schwarz space of distributions, provided certain conditions hold. So they have to belong to a certain subset. In particular, they have to have rapid decrease. Unless this random field Z is 1, they should be non-negative, Schwarz distributions. And you need a sort of square integrability conditions like you would need for any Ito integral. And so that condition is written here. Here I have the spectral measure of the noise. Here I have the expected square of the process, supreme over x. And this expression should be finite. Okay, so this is an extension that was developed with the wave equation in mind. And it allows you to handle the linear wave equation in all the spatial dimensions. So, because in that case, the process Z here is 1. And the nonlinear wave equation in dimensions 1, 2, and 3. So we've gained 1 dimension with this extension. Now we have at least 2 integrals, right? We have the integral with respect to spatially homogeneous noise, which you can interpret as a cylindrical Brownian motion and use that integral. Or you can interpret it as a worthy martingale measure and use the integral with respect to martingale measures. So what are the relationships between these 2 integrals? And I find it nice that the integrals produce the same result. Okay, so if you take the Walsh integral with respect to the martingale measure you've built from spatially homogeneous noise, or the integral with respect to the cylindrical Brownian motion that you've built with respect to, built from the spatially homogeneous noise, you'll get the same result for objects that you can integrate in the Walsh sense. And for objects that you can integrate in the extended sense, you'll also get the same result. Okay, so that if you want to use the general theory of cylindrical Brownian motion, you can. If you want to use specific facts that are related to the Walsh integral, then you can also do that. I want to mention one further extension that was developed by Quer-Sardanyons and Nuillard in a series of papers, not all by the three authors, by the way. This is an extension to Hilbert-space-valued integrals. So the integrals up to now were always produced real-valued random variables. Here, their motivation was to use Malliavin calculus, which sort of naturally produces objects that take values in a Hilbert space. So think of a Hilbert space, another Hilbert space H, right? I already had the Hilbert space U. I take the tensor product of U and H. So an element of the tensor product is essentially a matrix. A matrix where I take doubly indexed set of components, and I want the sum of the squares to be finite. And this is interpreted as an element of the tensor product by taking a sort of formal basis, EJ tensor Fk, where the EJs form a complete orthonormal basis of U, and Fk a complete orthonormal basis of H. And the xjk's are just real numbers. And the norm in this tensor product, I should have a U here, is given by the sum of the squares of the entries of the matrix. And so here, the objective was to integrate square integrable functions with values in this tensor product. Okay, so functions that would satisfy a condition like this. And so the natural way to do this, so the result of the integral now is an element of the Hilbert space H, is just to give the coordinates of this element in the basis Fk, basis of H. And so what are the coordinates? The coordinates are stochastic integrals, which you can think of as a Walsh, Dalang, Nuillard, Quer integral, or with respect to a cylindrical Brownian motion, of what? Of this object, which is just obtained by taking a column of the matrix. So here I'm taking the entries of the matrix times basis elements of U and forming an element of U. So I integrate that in the sense I previously defined. That gives me one component that I multiply by the basis vector Fk, and now I have an element of H. Okay, so the result of this integral is an H-valued random vector. And what can you define with this? What sort of objects can you integrate? So here I have a gamma, which takes values in the space of Schwarz distributions. It should be a non-negative distribution with rapid decrease and should satisfy this square integrability condition. And furthermore, it has to be a non-negative measure of this particular form, so absolutely continuous in time and a measure in x for fixed t, which has total finite mass. And now, before I had a process z, now I have a process k, which is h-valued. So I'm going to integrate h-valued processes, provided their L2 norm at least is finite. And so these are the sorts of objects you can integrate. So I have k times gamma. This is a process, so that's part of the statement, with values in the tensor product u times h. So I can define the stochastic integral, and it satisfies an inequality of this kind. The LP norm, now norm in the Hilbert space H, is bounded by this expression, which sort of looks like the expression we had previously for the real valued extension of the Walsh integral. Here I have the H norm in the Hilbert space of the process K, and this other integral with the spectral measure of the noise. And this is useful because we want to integrate the Malliavin derivative of the solution to an SPD, and that Malliavin derivative typically satisfies another SPD, which is naturally takes values in a Hilbert space. And so this now works for the Malliavin derivative of the solution to the heat equation in any spatial dimension, or the wave equation in spatial dimensions 1, 2, and 3. Okay, so this is all for school A at the moment. Now school B. School B, again, I have Krylov-Rozovsky to Prato and Zabczyk. So Hilbert space-valued integrals. Here the central notion is Hilbert space-valued Brownian motion. Okay, so let me just say what that is, or recall what that is. We're given a separable Hilbert space V, a linear, symmetric, non-negative, definite, bounded operator Q, which can have finite trace or infinite trace. For example, for the identity, the trace will typically be infinite. We take a complete orthonormal basis of V that consists of eigenvectors of Q with associated eigenvalues lambda j. And now we take a sequence of ID real-valued Brownian motions, and we define this object here. So we take the square root of the eigenvalue, lambda j, times the Brownian motion, times the basis vector ej. And so in principle, this will give you a v-valued process that will be called a v-valued Q-Wiener process. But this series only really converges if the trace of Q is finite. And so when the trace of Q is not finite, it's called a, quote, v-valued cylindrical Q-Wiener process. Yes, as I mentioned here, when the trace is infinite, the series does not converge in V, so you have to do something. This is sort of the elementary form of the second quantization that Boris Rozovsky was mentioning yesterday, is you sort of change the weights. These are basis vectors with norm 1. You change the norms of these vectors, and then the series converges, and you're happy with that. We want to define stochastic integrals. What can we integrate? So here you integrate Hilbert-Schmidt operators. So for positive numbers s, let phi s be a Hilbert-Schmidt operator from V into H. And we're going to integrate phi t dwt. Okay, so Hilbert-Schmidt operator times dw, w being the Hilbert space-valued Brownian motion. What can you integrate? You can integrate operators that have a finite norm where the norm is this one. So I have a Hilbert-Schmidt operator. I take the Hilbert-Schmidt norm not as an operator from V to H, but from Q to 1/2 V to H. And the first time a student sees this, they're always a bit surprised with this Q to 1/2. But anyway, it has to be there. And this is just an explicit expression of that norm. I didn't define the stochastic integral here. I just said these are the sort of things you consider. And the definition usually is a little bit different when the trace is finite and when the trace is infinite. You have to do a separate step. But there is this nice formula that works in principle in both cases. So I take a complete orthonormal basis of H. If I have a family of Hilbert-Schmidt operators, integral in the sense just mentioned, then the integral, you could define it using this formula, which works both when the trace is finite and when the trace is infinite. This is not what's usually done, but it's sort of nice because it means that this integral is really just a sum of ordinary Ito integrals. So the beta j's are just standard Brownian motions. Once I've evaluated phi at this vector and taken the inner product, I just have a real valued process. I integrate that with respect to my ordinary Brownian motion using an ordinary Ito integral. Add that up, sum over j. This gives me now a random variable. I multiply by the basis element fk to get something in the Hilbert space, and add that up. That gives me now a Hilbert space-valued object. Again, if I want to use this for spatially homogeneous noise, I have to first translate spatially homogeneous noise into this framework. Okay, so I have to build a Hilbert space-valued Wiener process from cylindrical Brownian, spatially homogeneous noise. So as Hilbert space, I'm going to take U star, so the dual space of the space U I've discussed earlier. Q will simply be the identity operator. And I've built the cylindrical Brownian motion associated with spatially homogeneous noise. And so now I define a Hilbert space-valued Brownian motion for what will be such, called W star, as the linear map H goes to WT of H. So for fixed T, this is a map from the Hilbert space into the real number. So I can think of this as an element of the dual space. That's why I'm taking V equals U star. So W star script evaluates against H, element of the Hilbert space, gives me a real valued random variable. So this is fine, except that since the trace is infinite, the process doesn't really take values in U star. But again, that's sort of a detail. And what we've constructed now is a cylindrical standard U star valued Wiener process. Okay? And now I'd like to have the relationship between the various Hilbert space-valued integrals that I've mentioned. So one being this sort of extended Walsh integral, which took values in a Hilbert space, and the other being this Krylov-Vazovsky to Prato and Zabczyk integral. So in approach A here, if you recall, I said that we integrated tensor product valued processes. So these were processes with values in VQ tensor product H, VQ being built from V by changing the inner product. And in the other approach, you integrate Hilbert-Schmidt valued processes with values in this particular space. So I don't know if these look similar or different to most of you. But it turns out that the tensor product is isomorphic in a natural way to the Hilbert-Schmidt operators from V star Q into H. And V star Q is exactly Q to the 1/2 of V. So that the tensor product space is exactly this space of Hilbert-Schmidt operators that you can integrate in approach B. And so I think this is an observation that had not been made previously by the people who are developing these integrals, but it's the following. So if I take an object that I can integrate in the sense of integrals with respect to Hilbert space-valued Wiener process, from that I can form in a natural way an object that takes values in the tensor product by doing the operation here. So I have my Hilbert-Schmidt operator. I apply it to root lambda j, inner product with fk, inner product in H, gives me an object, and now I form here an element of the tensor product by this sort of matrix type object. And the conclusion is that these two integrals are then equal. So on the left-hand side, we have this extended Walsh integral. On the right-hand side, we have this Krylov-Vazovsky to the Prato and Zabczyk integral. Okay, so the two integrals give the same result. This is sort of nice, I think, because the Hilbert space-valued integrals on the left were developed for very different reasons than the Hilbert space-valued integrals on the right. On the right, I think people were mostly thinking of L2 space, Sobolev space, and so on. And here people were thinking of Maldiavan derivatives and that sort of thing. But in the end, the two approaches give the same result. Obviously, the one on the right-hand side is much older than the one on the left. What do these give if we're trying to solve now stochastic partial differential equations? Let me think of the wave equation in spatial dimension 3, because for some reason that's the case I've been most interested in. It will also apply to the heat equation and the wave equation in lower dimensions. A mild random field solution is a real valued adapted process. So a random field defined for every t and x in space-time that satisfies this integral equation. So as you recall, I0 was determined by the initial conditions, and I've written down the explicit expression in the case of the wave equation in spatial dimension 3. So u0 is the initial value, v0 is the initial velocity, and we integrate with respect to the surface measure here on the boundary of the ball of radius t. So for other equations like the heat equation or wave equation in lower dimensions, you'd have a different formula down here. But in principle, you'd have the same formula up here, gamma being g, actually the fundamental solution of the equation. Okay, so this is sort of the equation you want to solve. And the theorem that does that is the following one. So of course, you need some conditions, most notably on the spectral measure. Remember that for space-time white noise, you will typically not be able to solve the nonlinear equation, and the linear equation you will not be able to solve it as a random field, but only as a generalized random field. And so the necessary and sufficient condition actually that allows you to solve the wave equation in spatial dimension 3 is this one. So I have to integrate 1 over 1 plus modulo psi square has to integrate against the spectral measure mu. And so there also has to be some conditions on the initial values. And in that case, you'll have a random field solution, so a solution that's defined for every t and every x. It'll be L2 continuous, and it will have finite piece moments for any p. Okay, so for fixed t and x, I'll have a real valued random variable u of tx. If we think of stochastic PDEs from school B, so they're usually written like this. So the first time you see that, it looks a little bit different from what was written previously. Let me just run through this, which is very, very classical. I have a cylindrical Q Wiener process on the Hilbert space V, an initial condition little h, which is in the Hilbert space capital H, functions f, a function f from h to h, a function b from h to linear operators from u to h. And here this A is the infinitesimal generator of a strongly continuous semigroup S of t. And so a generic solution will be an adapted h-valued process, so u of t. So for each time t, u of t will be h-valued. It is called a mild solution if this expression is satisfied, if this equation is satisfied. And so, yeah, here we're using the Hilbert space-valued integral with respect to Hilbert-valued Brownian motion. If you particularize to the wave equation in spatial dimension 3, again, you have these first two terms which correspond to the I0 of tx that I had written before, so related only to the initial conditions, initial position and initial velocity, and you have this convolution integral. Of course, here you have to choose the Hilbert space H, and you sort of have to interpret this object here as a Hilbert-Schmidt operator. And so, you know, a choice that was made, and I'll give the reference in a minute, is to take h, the square integrable functions, with a weight. And so the weight theta should be smooth, positive, even, and exponential decay. And now you have to interpret this object as a Hilbert-Schmidt operator, and this was done, at least for the wave equation, I believe, by Prato and Zabczyk, which says if you take an element u of this space L2 theta, then this object can be interpreted as a Hilbert-Schmidt operator from u star into L2 theta. And once you've done that, again you have a theorem for existence of the solution to the wave equation in spatial dimension 3. So here the initial conditions are taken to be initial position in a Sobolev space, initial velocity in an L2 space, sigma's Lipschitz, same condition on the spectral measure, and there is a unique solution with values in this Hilbert space L2 theta. Now for each fixed time, the solution u of t is a function of x, so it's defined for almost every x. Okay, so now we have two ways of solving the wave equation, by the school A approach or the school B approach. We'd like to see the relationship. Now, in general, each person starts with their own object, their own Wiener process or their own martingale measure. And so the solutions are not living on the same space, and you could only compare the law, for example. But here, I started with a spatially homogeneous noise, and I built first a martingale measure, then a cylindrical Wiener process. So I started from the same object and built two others. Okay? So, in fact, the solutions now can be defined on the same probabilities. They are defined on the same probability space. And so, they're just random objects defined on the same probability space. I can compare them. And so the result is the following. So for the stochastic heat equation in all spatial dimensions, the stochastic wave equation in spatial dimensions 1, 2, and 3, on the one hand, we have the random field solution produced by the school A approach, u of tx, defined for every t and every x. And so what you can do now is for fixed t, let x vary, so consider the function u of t, which is x goes to u of tx. And this produces now a function for each time, and this function is the L2 of theta valued solution. Okay, so sort of comforting that both approaches produce essentially the same solution. So let me just conclude by saying that many integrals that have been used over the last 30 years are closely related. We've seen some that are equal or equivalent. And I guess one goal of our paper is to help those who are using one integral. They want to maybe quote results from another paper that uses a different integral. Do they really have to check that they're using the same object or not? So at least in certain cases, I hope that our paper will save them time, and they'll just be able to say, well, that object actually is the same as the one we're considering here. I think that's one objective. And let me just give some references. So we have the paper my talk is based on here is available. It's Stochastic Integrals for SPDEs, a comparison. I've just listed some of the main references here that we use to prepare our paper. Of course, there are many others, so I've listed here Walsh's lecture notes, a paper of mine, the book of Martin Saint-Soleil, which contains one of the initial developments of the Hilbert-space-valued extension of the Walsh integral, a paper of Newellart and Lluis Quer, and then here the books of Krylov-Rozovsky, the Prato and Zabczyk, and the Peshat-Zabczyk papers that dealt with the wave equation in higher dimensions. Thank you for your attention.
Question.
I have a comment and a question. You write Krylov-Rozovsky 79 in Russian. It was translated almost immediately. So
Okay.
don't be scared if you want to read the paper. There is English, Russian.
Okay, I'm aware it was translated.
You are also.
So I mean, the first English reference that I saw, I looked maybe too quickly through Math.net, I think was 1990. But the Russian version was 11 years earlier.
No.
No?
It's not a book. It was.
It's not our book. It's actually not our book. It's a paper in a book.
Okay.
And then the question is, did anybody try to use approach A to represent measure-valued branching processes, super processes, the solutions of SPDE in multi-dimensional case, not in case D equal to 1?
In multi-dimensional case, that I don't think so. Or at least I'm not aware of it. So certainly in spatial dimension 1, I would say the Perkins, Vancouver, and so on was in Walsh and so on, already Walsh.
But in multi-dimensional
Multi-dimensions, I don't think so. At least I'm not aware of that.
Did you study boundary value problems for these equations also?
Okay, no, we didn't. So yeah, these were equations defined on all of RK without boundary values. Yeah, so we stopped at that.
Other question? I have a question. If one is interested in space homogeneous solutions, you have a paper for verification. Which approach would be better?
So I said I was not trying to say that one approach was better than the other. And in the end, I think neither approach is better than the other. That is, when you actually look at the estimates that you have to make, essentially you're making the same estimates. You're just framing them in a different language if you want. So I think if you've learned one school, you'll find that easiest. If you've learned the other, you'll find the other easiest. But it will remain subjective somehow.
But if you use the approach A, you can get the regularity in space and mild conditions. If you use this approach B, you can get L2 solution or sublevel solution. So you can get more, mild, regularity for Holder continuous X in space. Use approach A under quite mild solution, mild conditions only.
The approach A produces a U of Tx for every T and every X, and that's a small advantage. But as soon as you start studying, I would say even Holder continuity, you can go by the Kolmogorov continuity theorem, or you can go via the Sobolev embedding
Yeah, so
theorem.
then you need more conditions on coefficients.
But it's essentially equivalent. So, for example, Martha and I did this explicitly. Martha and I did that explicitly for the three-dimensional wave equation, and the two are, I think, essentially equivalent.
In fact, Kolmogorov's continuity theorem itself is an example of Maury's version of Sobolev embedding. So you really are talking about a series of equivalents.
Other questions? Thank you very much.